Thank you. Thanks for the opportunity to talk about this topic and during this week. So the main object of this topic is something called q-Pochhammer symbol. So first I have to introduce what it is. So the Pochhammer symbol is just a short name for something which is a convenient way to denote things in combinatoric and binomial coefficient. So I'm not at all an expert on combinatoric. This is just, but I need to introduce the name because that's a name for it. So, okay, so the quantity which will be interesting for us is not exactly this one, but a Q variant, a Q analog, which is the following one. So A and Q are complex numbers. And then the notation in combinatorics is the following one. There won't be much combinatorics in our work. It will be good complex analysis and this kind of thing, but let's see. So this is the quantity. So there are many identities and generalization of binomial coefficients, which make sense when you replace formally the Pochhammer symbol by q-Pochhammer symbols. Some formulas remain true. More precisely, what the things which will be recurrent in this talk is this one. When you set A equals to Q. So then we forget about the A. So Qn will be when we set A equals to Q. So it's the product of the powers 1 minus Q to 1 minus Q to the n. So here n is an integer greater than or equal to 0. If n is 0, this product is empty, it's equal to 1. Okay, and Q can be anything, of course. So why are people interested in this? So there are many reasons. I will quote 4 connected ones. So it appears in partition-related appears. Okay, my handwriting usually is bad. Now it's even worse. Appears in, if you can't read the word, please tell me. If it appears in partition related generating series. So I will quote some. So of course there is a partition function. The number of ways to write an integer as a sum of positive integer. So it's denoted P of n. And this generating series is nothing else than, so it's easy to see if you group all the components of the sum together, it's an infinite product. And this is just, you can denote formally by, so it's just Qn, but then you take the limit as n tends to infinity. So here Q has to be of modulus less than 1 for this formula to make sense. And this product is useful because, so for instance, you can obtain Hardy-Riemann-Johns, okay, the theorem on the asymptotic formula for P of n by exploiting the polar behavior of this product on the unit circle. There are many works in finding identities. On finding identities between Q series. So it's a big business. I will quote one, which is called the Rogers-Ramanujan identity. Which is the following. So if you take this summation, some q to the n squared divided by this symbol that we had before, then it's equal to the product resembling also involving the q-Pochhammer symbol, but this one extended to infinity. So now I need to use the other notation with the A. It's a product like this one, but restricted with congruence condition on R mod Q, mod 5, sorry. Q to the 4, Q to the 5. Okay, another interested is that it's connected to the connected to a modular form, a particular modular form. So it's a function eta defined on the upper half plane. Okay, this is z of imaginary part bigger than 0, which is so E of z over 24 times the Pochhammer symbol extended with n going to infinity. And E of z here is the one periodic e to the 2 pi I z, the one periodic exponential function. So saying that this function is a modular form, yes, so imaginary part of z is positive, so this number is of modulus strictly less than 1, so this makes sense. And saying that it's a modular form for this specific function means that it satisfies some identities. So because of course this is one invariant, when you shift z by 1, you would just have a factor coming out, which is E of 1 over 24 times eta of z. And eta of minus 1 over z is z over I to the 1/2. So z over I has a real part positive, so you take principal determination of the logarithm times eta of z. So, okay. So closer to what I'll discuss today, there has been another line of research was devoted to study sign products. So this is understanding the size as a complex number. The size and distribution of values of the Pochhammer symbol when the modulus of Q is 1. Okay, so when this happens, of course, we have that this thing has modulus between 0 and 2. And note that, okay, so oops, sorry. Okay, use this. And okay, so I recall the definition. This is the product from R from 1 to n of 1 minus q to the r. So if you try to imagine this as some kind of Riemann sum for some function, we notice that the integral between 0 and 1, if you imagine that all these powers, that q is a number, a typical number in the unit circle, then all these powers will become uniformly distributed. And when you take the logarithm of this, you notice that the modulus, the moduli tend to compensate each other. So because this holds, there is a lot of cancellation. You expect that for typical Q at least, some cancellation happen in this product. So the size of this product relates to the secondary terms in this Riemann sum approximation. And so this is a fact that makes this problem, tends to make this problem somewhat difficult. Technically. So I mentioned some names. So there are works of Erdős and Székely, like in the 50s, I think, followed by work of Sudler in the 60s. So for instance, one of their theorems, the theorem of Sudler, I think, is the fact that if you fix an n and you compute the maximum of this symbol on the circle, then this is exponential. There is a constant such that this relation holds. So it's n to some power times an exponential growing. So k is some constant. mention some further names. So Lubinsky has studied this problem, and for instance, one of the theorems that he proved is that for typical Q for Lebesgue, almost all Q on a unit circle, the size is actually much less than this. It's not exponential in n. It's O of log n to the 1 plus epsilon for any epsilon. And for Q radius 1, Q almost everywhere for Lebesgue measure on the unit circle. One further work, which is, okay, so this is 1990, some further very recent work, very nice theorems. This has been revived very recently by Grepstadt, several authors. So Grepstadt, sorry, with a D, oops, I apologize for this. Kaltenbach, which are in Norwegia, I think. Neumüller from Linz. And then there are 2 or 3 works with 2 or 3 of these people, then followed by further work joined with Eisleitner, Christoph Eisleitner, Niklas Tekno, and Feopoulos from Graz, and Benz Border. So for deterministic, they study deterministic Q, so fixed Q. Deterministic is a bit over. And especially for Q equals the exponential, and so on the unit circle with the angle which is quadratic. A quadratic number. So for instance, what a theorem of Grepstadt, Kaltenbach, and Neumüller is the following from 2019. The q-Pochhammer symbol at the golden ratio is bounded below by 1 and upper bounded by n. And this was open since it's a question which was asked by at least Lubinsky, but from before. So. Okay, so so why we started to study this function, so before we knew about so many of these works, with Sandro, we were studying a paper by Zagier. That's the fourth motivation. And in this paper, I will put this the reference, so Zagier 2010. He has a paper which is called Quantum Modular Forms, in which he studies many functions, and there is a very funny function in there, which is related to knot theory. So we don't know anything about knot theory, but the function is not very complete. Well, at least not very complicated to write down. So I'll say it. It's also the q-Pochhammer symbol is also a basic component in constructing quantum invariant, quantum knot invariant, and also no, not only for knots, but so Jones, and for us a name which is associated with this in knot theory is the Kashayev invariance. So I won't try to draw a knot, because this is for knot theory people. I would fail miserably, but so a knot is a diagram, okay, with some crossing. It's a knot in 3 dimensions, but you can represent it in 2 dimensions. It depends on skills which I don't have here. And to a knot, K defines a knot. When you draw it, you can, when you look at the diagram and the crossing and which part of the knot goes onto another, and you look at some combinatorics, and from this you can construct some invariant. So Kashayev associates a function which, so I will state two examples to show you what it looks like, to make it a bit more concrete. So 5.1 and 5.2 are some knots. I can try to, maybe I can show them to you, but after the talk, because I need to find them online. I didn't think of drawing them. I'm sorry about this. Which depends on the variable q. And so, for instance, in one of the most simple cases, the function is the following. You sum from n from 0 to infinity the q-Pochhammer symbol modulus squared. Okay, so this is just, you take the product. For n equals 1, the product is empty, and otherwise you take all the successive 1 minus q to the I modulus squared. Okay, so if q is modulus then less than 1, this of course diverges. If q is modulus bigger than 1, it also diverges. But when q is modulus exactly 1, the interesting case for us will be when q is when q is exponential of a rational x. So it's a root of unity. So when q is a root of unity, eventually this product will vanish, and so this sum makes sense for a trivial reason. So this, I will state another one because I will need it. It's to illustrate a later statement. So this one is a bit more complicated to write down, but it's to show you that sometimes the sounds are not always positive. Okay, q bar n times modulus qm squared. So now it's a double sum. Sorry, there's no x there, it's capital N. And what is capital N? It's the denominator of x. It's the order of q as a root of unity. Okay, so, okay, maybe strictly less here. Otherwise, there is a definition trouble. All right, so why was Kashaev interested in this invariance is that it's easy to compute given the knot, and when you look at some asymptotic expansion of this knot, they will tell you information about the knot itself, about the geometry of the knot, and this is something that interests knot theory. But the reason why we're interested in this function is that, well, it's a very simple looking function. It involves the Pochhammer symbol. And there are many things that we still don't quite know about this function. So here's a statement. It's called the volume conjecture, but it's actually a theorem. It's not a theorem still. It's a theorem in some cases. And the cases that I'll talk about today, it's a theorem. But for generic knot, it's still wide open, and the knot theory people are very. It's an important conjecture. It's wide open conjecture there. So when you look at the first root of unity, and you let the order tend to infinity, then they expect that for any such invariant constructed from the knot, and especially the two that I wrote above, there will be an expansion like this. So it will be exponential in n, with ck is some geometric invariant using the knot and divided by 2 pi. So it's some constant, which has a geometric meaning that I won't discuss today. Okay, but then, so this doesn't tell you what happens for other roots of unity, and this is one of the first questions which motivated us. So we're very happy to try to understand this. So you let and a rational be given. It will be between 0 and 1. Maybe like this. And okay, I will write what will come here afterwards. But what we want to know is what's the size of J for one at E of x for other kind of rationals. And we can answer this question under so a generalization of this theorem, which is a theorem of I will state the names afterwards. Of Anderson and Hennenfent, in the case of 4-1. We can generalize this statement for other rational functions. So this simple looking function from before, when you evaluate it as a at other rational, it will take the following form. Of course, there is a specific constant here, plus little o of 1 times a quantity which will depend very simply on the on x. Well, simply yes and no. It's the continued fraction expansion of x. And so this, if you use a classical notation for the continued fraction expansion, r is the length. And this asymptotic formula is as the mean value of the AI tends to infinity. So if I give you a sequence of rational numbers with their the mean value of their coefficients tending to infinity, you will get an asymptotic formula for the log of the J invariant. For this case, for the note, this note. And so we're very lucky here because this is typically the case. Okay. If you take 1 over n, it will you obtain back this statement. But this in fact holds for many other rational numbers, and actually almost all in a certain sense. So that's a corollary. As q tends to infinity, for a proportion 1 plus little of 1 of rationals of x with denominator. Oh, so, okay, I won't be using q for the denominator. I need to stop doing this. Of denominator less than q. So when you average over all rationals less than denominator less than q, when you pick one at random, then for almost all of them, you have the asymptotic formula that this thing is exponential of, so what I wrote before, but it turns out that that for almost all rationals there is a simple law of large numbers. Well, okay, simple to state, but to prove it you need to work a bit harder. So we obtained a law of large number with Sandro for the sum of the continuous fraction digits, and from this we immediately deduce. From this and the previous theorem, you can immediately deduce this statement. So it's a form of law of large number for the log of the J invariant of rational numbers. So you can ask about this condition. Is it necessary or what? And well, we're so very happy because Christoph and Benz, Christoph Eichleitner and Benz Borda, earlier this year, they obtained a very nice statement, which I'll state now. So the condition this condition is actually necessary because of the following theorem of Christoph and Benz, that so you take one example of a number which a very simple example, the simplest example of a number for which the average doesn't go to infinity is when you take all the AI equal to 1. And so if you fix for any n, x being the rational with all the numbers equal to 1, and I will say more about what they can do, what else they can do. So this is a quotient of 2 Fibonacci numbers. And for these numbers, so this depends on n, then the j function grows exponentially, exactly like before, but now the constant is different. So this is the same sum, the sum of the AI, but now the constant is not the same. Okay, I can hide this. The constant c is 1.1 something, at least, well, okay, numerically. They show that numerically it seems that the function is like this. Maybe they have some proof that the first digits are this, but I'm not sure. Maybe Benz can answer if he's around. But they show that this constant is different than the one from the almost all results above. So the result is much more general, and in particular, it works for all quadratic irrational. So when the expansion is periodic, they can answer this. They can obtain this formula, and the constant is not it's not always the same as before. More general. X which are quadratic. Okay. So now I'll explain a bit why all of a sudden we were talking about this Pochhammer symbol, and then we got into continued fraction expansion. So before this, maybe I can stop for a few instants and ask if there are any questions. There seems to be one. Oh, no, that was Antoine. Okay. If there are no questions,
there's no question at the moment in the chat. So maybe someone will arise questions.
Okay.
Seems not the case, so please.
Okay. Then I continue. So why is the continuous fraction expansion relevant here? Continued fraction expansion. So that's because of a conjecture by Guillaume, who observed numerically the following. So you let h of x be, so I will state it only for the variant that I mentioned before. H of x be the log j. See, everything happens inside the log. So let's take the log. Log j of that function from before at e of x minus log j, same thing as before, at e of 1 over x. Then this function, which is defined on Q, is extended to a nice function of x in R, R star. So what I mean by nice is, well, not very clearly. The best way I can illustrate this is by showing you a picture. So this is Zagi's paper, Quantum Modular Forms on 2010. It has lots of stuff, 17 pages, but still has lots of stuff. And he has the following two graphics. So this is a log of the function that we had, plotted at rational numbers. We can see the size grows, the denominator grows. And then it doesn't look so regular, but if you take the difference between the difference that I just wrote, you obtain this function, which is, well, okay, at least much nicer looking. It's not very clear what we conjecture, but by zooming in at a rational, we see that it has some jumps at rationals. So certainly we don't expect it to be continuous. And at irrational numbers, so 1 over phi is here, the golden ratio. And you see, well, okay, it looks continuous. It's not so, it doesn't look at all differentiable, but at least we can imagine that the function has a limit. The limit is close to 1.1, and this is related to the value that I showed you before. So let's see, sorry, this one. So let's see, h of x, it looks continuous near the golden ratio, or the inverse of the golden ratio. And h at the golden ratio looks close to 1.1, and this would explain the theorem that I showed you before, the theorem AB. Okay. Let me call this one the generic theorem. And secondly, let me get back to this function. You see, it goes to infinity, and it seems to go to infinity like 1 over x numerically. You don't have to believe me on this. H of x seems to grow like the constant that I showed before divided by x, as x goes to 0 plus. And this would explain the generic theorem. So, oops, sorry. Sorry about this. So it would explain the theorem that I called the generic theorem. So why? Well, this is because when you start with evaluating the function at a certain rational, when you replace x by 1 over x, because this is one periodic, at each time you apply you replace a continued fraction. Oops, sorry, I should take the log. You replace the continued fraction. So say this is x, or you get h of x plus, so log j of 1 over x, but 1 over x modulo 1 is just taking away the first coefficient. For 1, 0 of e of 0, a2, ar. So if the first coefficient is big, it means that x is very small, and then this will look like c for 1 times a1. Okay, and then when you iterate, you get c for 1 times a2. Well, of course, these numbers have to be big for this to make sense, and we can only prove this when the average goes to infinity. Okay, yeah, maybe I can keep this actually. Okay, so I have a little time to explain to you yeah, I still have maybe 15 minutes, so I will say to you what happens inside the, well, what is the main theorem that is driving everything. So we don't have this conjecture. If we had this conjecture, things would be much easier, and also with this information, but we get around this conjecture. By proving two theorems, which are modularity looking, a modularity relation much like the one I wrote before for eta. Let me go back to it for an instant. If much like this one, but having to do with the Pochhammer symbol. So the main theorem is that, so there are two. If I give you for gamma in SL2Z, then the function which to x and n associates e of x over 24. So this is in Q cross natural numbers. Well, actually cross. So let's see, 0 denominator of x minus 1, because then it vanishes afterwards. Let me see. So e of x. So then, so this function, which is interesting for this value, x is rational and n varies between 0 and the denominator of x minus 1, satisfies it satisfies a transformation formula which okay, maybe I can show it to you if you want, but it will take some time, so I will concentrate first on this informal description. It's a formula which relates x, which sends x to gamma x, like a modularity relation, and it sends n to, let's state it like this. Yes, it sends n to the floor part of n divided by denominator of x times the denominator of gamma x. And this is a number between 0 and the denominator of gamma x. And this formula is exact. Zero term depends holomorphically on the following, on the fractional part of this number. So I have to explain to you what I mean by this. And yes, maybe I have time. It will take, I think, some 5 minutes more to explain the full statement of this theorem. So the first part, the formula that we have, I can show it to you. Actually, I'm wondering. Okay, it takes some notation, so more precisely. But the point there is a point I want to make in this formula. And to make the point, I need to actually show the formula. But the formula is not very, not particularly good looking. So to state it, I need to, okay, I don't need alpha. Right, x as a rational, and gamma of x. Here is gamma of x. You can express it using nd and all this, but for us it will be h over k. Then for 1 less than r less than k, if you let L to be the floor part that I wrote before, and lambda to be the fractional part that I wrote before, if you take the quotient between these two things, then this will be an we can express this exactly as sum of many terms. There is the first one which will be maybe ring a bell for people who study cotangent sum. So this is a Dedekind sum. Plus pi I over 4 plus half log of k over d. I will explain each term. Plus k over qd times some function which is related to the logarithm, evaluated at this number between 0 and 1, plus an error term which depends on r, lambda, and d over k. And the main point is that this error term is holomorphic in, it's a function which depends on L, on lambda. And when it has an expression depending on lambda, which makes it extendable to a holomorphic function in lambda. So in this set, let me see. Okay, whatever. It's some other set, more general than this one. And this came as a surprise because all these are finite products. So it's not, maybe it's not, it doesn't come immediately as a surprise that such a formula exists, because when you take r going to infinity, if you could, you would obtain the Dedekind, the eta function that I wrote before. And the eta function is a modular form, so okay, you might expect something like this to exist. But this is not the infinite product, it's a finite product. And even by taking finite products, you can still, you have still a formula which is useful. And it's useful for us. And this is relevant. It's relevant for us when the denominator of x is bounded. This is a case when we can control the error term. And there is a second ingredient, important ingredient that I want to mention in the previous theorem, which is a second relation formula. Now, okay, I won't state it, but there is a second reciprocity formula. Okay, modularity. Sorry, modularity formula. Second modularity formula. Which relates. Now it's a bit. There is another layer of complication coming from the fact that it doesn't relate x with gamma x or 1 over x. It's going to relate the gamma x bar, which is when x you write it as an irreducible fraction. X bar which be you inverse the numerator modulo the denominator. Of course, this depends. This is only defined modulo k, so we take fraction apart. There's a formula which relates this, and basically it means that when you apply, it allows you to take away not the first coefficient when you're making Euclid algorithm, but the last coefficient. This transformation going from x to x bar is equivalent to reading the continued fraction expansion in the reverse order. And there is a reciprocity formula which relates these two for the q-Pochhammer symbol. And it's useful for us. So I'm going to lie a bit to make the point more clear. It's useful for us when the denominator of x goes to infinity. So it's actually, it depends on the way you state it, but the way to state it which makes it useful when the denominator stands to infinity. And this is precisely the complementary case of the previous one. So if we could get rid of this condition, we would be getting very close to the Guess conjecture. We cannot, we're not able to right now. But by proving this complementary modularity formula, which has a lot of disadvantages, but it has the one big advantage that it's useful as soon as the denominator goes to infinity. And by combining the two, we can successfully iterate the formula. where we want. And maybe I can finish with a last remark that in this formula, in the formula 2, there are some peculiar objects that pop up, which are the following. It's a cotangent sum. So let me say, okay, by n, k, k bar over h, maybe. Oh, sorry. Okay, sorry. I confused between the button for go back page and okay, cotangent of pi n h bar over k. H inverse over k. This function is one periodic, so this makes sense, modulo k, times n over k. And if the sum was over all residues, non-zero residues modulo k, this would be a cotangent sum. But in this formula, it turns out that very naturally, I mean, we certainly didn't call for it, that this sum appears when R is restricted to be something else to the k. So it's a partial cotangent sum. And we struggled for a long time with this kind of object. It has some reciprocity, but it's not exact. So, okay, there is something. There was something new going on in this formula that we didn't expect. So if you stumble on something like this, maybe take a look at this at our paper or Lubinski's paper, and it might save you some headaches. Okay, so you can say more about some elements of the proof if someone asks, but otherwise I stop here. Thank you for your attention.
Yeah, Sary, thank you very much for this very nice Blackboard talk. So we could end this conference with a Blackboard talk. Of course, in Auditorium A1 at Cirm, we have much more Blackboards. We have 3 big ones and some smaller ones. Here is just one Blackboard, but it has one advantage compared to a real Blackboard one. We can go back to any Blackboard. So I have a small question. You introduced this geometric constants somewhere in the first third of the talk. Could you say some words on the geometric interpretation of that constant?
Yes, so maybe for this I can find a picture of the knot. So I need to find a picture of the knot. Let me see if it's in the Gibbs paper.
Because this interpretation as knots would be really very instructive.
Yeah, so let me get right back with the screen share. I need to find a picture of the 4-1 knot.
But if it takes too long, we should postpone it to discussion room or something like that.
It's okay, I found it. I just found
you
it.
found it.
It's actually on Wikipedia, it wasn't difficult. Okay, so let me see. Yes, so this is a figure 8 knot. This is the 4-1 knot that I was talking about. And when you consider the complement of the knot, so everywhere in the space except inside, it turns out, so there is a theorem of okay, I forgot his name. Okay, that's embarrassing. He's one of the biggest people in that thing. You can put a hyperbolic structure, metric, on the complement of the space, which makes it a hyperbolic space, and it has finite volume, and the constant is the volume of this space. You can
so maybe it's due to McMahon or
sorry?
Maybe it's due to McMahon. I don't know, but it could be. No? Okay.
Okay, yeah, I don't remember something. I'm sorry. It's not his one, but Thurston,
okay.
Okay, that was embarrassing. Yes, okay. So he showed that you can decompose the complement space into simpler hyperbolic space, and when you compute the volume, it's intrinsic quantity, and the constant is the volume of that.
Okay, so thank you for this very nice explanation. Are there other questions? Short ones, long ones are postponed to the discussion rooms. Yeah, Bence is typing a question. Maybe it will come soon. Yeah, can you read the question?
Yeah, is it conjecture that the guess function is continuous at every rational? And I believe so, yes. And it certainly looks so numerically. Of course, you have to be aware of the numerical, so I can show you why. This will be a funny explanation for that paper. And there is a graph from this paper. So this is what happen when you compare j of x with j of 1 over x. And this is what happen when you compare j of x bar with j of 1 over x bar. So it looks much or less the same. But this function takes actually, it goes to plus and minus infinity at the neighborhood of any rational number. So it looks to be nice and continuous, but when you zoom in, you remark that it's not, it's not very nice at all. Actually. So you need to be aware of conjectures, but I believe that h of x is continuous at every rational.